Nothing about this mission should have worked. A spacecraft reached Venus exactly on schedule. It arrived at the one moment it had been built for, then watched that moment slip away forever. The engine meant to slow it into orbit stopped long before the maneuver was complete. Instead of curving around the planet, its path bent only slightly before carrying it back into interplanetary space. Yet one thing never disappeared. The signal kept coming. The mission had failed, but something essential had survived. Inside JAXA's control room, the orbital trajectory looked wrong almost immediately. Engineers expected the line to wrap cleanly around Venus after a planned 12-minute braking burn. Instead, the projected path stretched beyond the planet and continued around the sun. There was no fiery explosion, no cloud of debris, only the quiet realization that the spacecraft had missed the only arrival opportunity it had ever been designed to use. Even then, the telemetry kept arriving. The radio signal remained weak but steady. Commands still reached the spacecraft, and responses continued to come back. Although it was no longer becoming a Venus orbiter, it was still very much alive. The silence inside Mission Control reflected a different kind of emergency. The question was no longer how to begin exploring Venus. It was why a healthy spacecraft had ignored its destination. The answer was buried inside numbers recorded during the opening moments of the engine burn. As engineers reconstructed the maneuver from telemetry, they found that the main engine had produced far less thrust than expected. About 2.5 minutes into what should have been a 12-minute burn, temperatures climbed well beyond normal limits. Thrust rapidly collapsed. The onboard computer shut the engine down automatically before even greater damage could occur. By then, the opportunity had already passed. The spacecraft had failed to slow enough for Venus to capture it. The engine itself was no longer usable. The damage, however, had not begun inside the nozzle, that eventually cracked. It started much earlier, inside a small check valve within the helium pressurization system. The obstruction restricted fuel flow while oxidizer continued entering the combustion chamber. That imbalance created an oxidizer-rich environment that drove combustion temperatures far beyond design limits, until the silicon nitride ceramic nozzle fractured under the extreme heat. The nozzle would never be used again. That discovery transformed the problem. Until then, engineers had wondered whether the mission could somehow be repaired. Now they understood that the spacecraft itself remained healthy, while the one system responsible for entering orbit around Venus was permanently gone. Power was still available. The instruments still responded. The solar arrays continued generating electricity. But the original flight plan no longer existed. Attention returned again and again to the trajectory map. Instead of ending at Venus, the line now looped around the Sun in a long heliocentric orbit. Calculations showed that this new path would eventually cross Venus again. Not in a few weeks. Not even the following year. 5 years later. On paper, another encounter was possible. Keeping the spacecraft alive long enough to reach it became the entire mission. That proved far more difficult than simply waiting. Akatsuki had never been designed to spend years traveling closer to the Sun than originally intended. During repeated passes through its heliocentric orbit, solar radiation climbed to roughly 140% of the level experienced near Earth's orbit. Every close approach placed additional stress on electronics, scientific cameras, and thermal systems built for much gentler conditions. There was no way to escape the heat. Instead, engineers found ways to manage it. Commands sent across millions of kilometers gradually changed how the spacecraft faced the Sun. Its large, high-gain antenna became more than a communications dish. It also served as a shield, keeping sensitive instruments in its shadow whenever solar heating became most severe. The routine repeated itself again and again. Adjust the attitude. Protect the cameras. Preserve the spacecraft. Scientific observations would have to wait. So would Venus. Another decision soon followed, and there would be no reversing it. Deep inside the spacecraft remained roughly 65 kilograms of oxidizer. With the main engine destroyed, that oxidizer had become nothing more than excess mass. Carrying it made every future maneuver more difficult, while keeping it offered no realistic path back to the original propulsion system. Engineers chose to discard it. The valves opened, and 65 kilograms of oxidizer vented harmlessly into space. The spacecraft became lighter. The main engine became irrelevant. From that moment forward, there would be no returning to the mission as it had originally been designed. Only a different mission remained. That shifted attention toward hardware never intended to carry such responsibility. Small reaction control thrusters occupied the corners of the spacecraft. Under normal circumstances, they made tiny adjustments to orientation and stability. They were designed for precision, not power. No one had built them to capture a planet. Before trusting them with that task, engineers conducted a series of carefully planned test burns. Each firing lasted longer than the last. Telemetry was studied in detail. Temperatures remained acceptable. Fuel consumption matched predictions closely enough to suggest that the impossible might at least be physically possible. The spacecraft no longer had a main engine. It had 4 small thrusters and 1 remaining opportunity. Meanwhile, the trajectory map continued to evolve. Every orbit around the Sun brought Akatsuki slightly closer to another meeting with Venus. Year after year, the spacecraft continued answering every command sent across interplanetary space. With each successful communication session, recovery became less a matter of optimism and more a matter of engineering. Eventually, the calendar arrived at a familiar date. December 7th. Exactly 5 years after flying past Venus, Akatsuki approached the planet once more. Everything now depended on 4 reaction control thrusters that had never been intended to perform an orbital insertion. The burn began. Unlike the failed maneuver 5 years earlier, this one demanded patience. The reaction control thrusters generated only a fraction of the force once provided by the destroyed main engine. They would have to fire continuously for more than 20 minutes, slowly reducing the spacecraft's velocity using hydrazine alone. Nothing dramatic unfolded inside mission control. The numbers changed gradually. Velocity decreased a little at a time. Orbital calculations updated continuously. With every passing minute, the predicted trajectory edged closer to becoming a closed orbit around Venus. Any premature shutdown would send the spacecraft drifting past the planet for a second and final time. The thrusters kept firing. 20 minutes passed. Then 20 minutes and 28 seconds. The calculations settled. This time, the trajectory no longer escaped into solar orbit. It closed around Venus, not in the compact 30-hour orbit originally planned, but in a vast ellipse reaching roughly 440,000 kilometers from the planet at its farthest point. It was nothing like the original design. It was enough. After 5 years in solar orbit, Akatsuki had finally become a Venus orbiter, using hardware that had never been expected to perform the job. Only then could the scientific mission truly begin. The orbit differed dramatically from the one engineers had planned before launch, yet it still allowed valuable observations of Venus's atmosphere. Cameras that had spent years protected behind the spacecraft's antenna finally turned toward the cloud-covered world they had nearly missed forever. The story is easiest to understand through one recurring image: the trajectory map. Its first version ends with a line drifting past Venus and disappearing into another orbit around the Sun. Its final version shows a long, narrow ellipse wrapped around the same planet. Between those two lines lie 5 years, 65 kilograms of discarded oxidizer, 4 reaction control thrusters, and a spacecraft that never stopped answering when every expectation said its mission was already over.